So now what we will do, we will consider two bodies which are at different temperatures, and there is heat transfer, which is obviously irreversible heat transfer. These bodies now, when they give out heat, the body which gives out heat, its temperature will drop. The body which receives the heat, its temperature will rise. So these bodies are they are not considered as source and sink, source or sink. So look at this. Let's consider this is a kind of heat exchanger. You know, heat exchanger is a device where heat transfer takes place from one fluid to another fluid. Here is gas which is flowing towards right and water is flowing towards left. Gas is the fluid which is giving out the heat to water. All the heat that is going from gas will be received by the water. As a result, the temperature of the gas will lower and the temperature of water will increase. Let's take some arbitrary values. Let's say that the gas is entering here at 1100 and it's leaving here at say 600 Kelvin. Okay, 1100 to 600. That's the drop in entropy of the drop in temperature of the gas. Let's say water is entering at 200 Kelvin and it is leaving at 500 Kelvin. So water is heated from 200 to 500. Okay. So all the heat that is given by the gas, when it drops, its temperature drops from 1100 to 600 Kelvin, is received by water and its temperature will rise from 200 Kelvin to 500 Kelvin. Okay. So this is what it is. Now what will the entropy principle tell you, right? See what will happen to entropy of the gas. Obviously entropy of the gas will decrease. Okay, and how will you find it out? You can say delta S of the gas. Okay, delta S of the gas. The expression which you will use is mCp of gas ln T2 by T1. What is T2? Final temperature, right? Which is 600. T1 is 1100. So it is 600 by 1100. Okay. So that will be the entropy change of the gas. What will be the entropy change of water? It will be delta S water, and that will be mCp, let's say m dot because mass flow rate we can consider, of water ln T2 by T1, final temperature of water upon initial temperature. This is final is, as it leaves there, heat exchanger is 500, initially is 200. So it is 500 by 200. Now this will give you the entropy change, right, of both the fluids. And because the heat transfer is irreversible, because this temperature, average temperature of this gas is higher than this is an irreversible heat transfer. Temperature difference is finite, so it's an irreversible heat transfer. So logically you can say this will be obviously negative. This will be with negative sign because entropy will decrease. It is giving the heat. This entropy is increasing. Okay, but again, increase will be more than decrease. So if you add these two, it will be positive value. That means this entropy generation in water is more than decrease. Okay, if the decrease here is 2 units, increase could be more than 2 units. If you just algebraically add it. So recollect what I did in the previous example. There we have considered two bodies of infinite heat capacity. Now here these two bodies are of finite heat capacities, and again the same principle, entropy increase of water will be more than decrease of this. Okay, more than decrease of this. If you want to show that on a TS plane, it will be worth exercise. Let me let me make a sketch. This is temperature entropy. Let's say we show the entropy change of the gas, right? When you show the temperature on the temperature entropy graph, that this temperature is dropping from 1100 to 600. And what is happening to entropy? Entropy is decreasing. So the process line will be like this. So this, let's say this is 1100 and this is This is the drop in entropy. Now this is the temperature profile. Now see, the drop in entropy will be this. Okay, this is the, we can say this is delta Sg. This is drop in entropy. Okay. Now let's show that for water. What will happen to water? Water is heated from 200 to 500. Okay. So let's say this 500. So I'll say some value will start say here, right? Let's say here this is 200, and it is heated 200 to 500. So it will be so this is, so the temperature, this was 600. Sorry, this was 600, and it is heated from 200 to 500. So here it is going to be heated from 200 to, now entropy is going to increase. Okay, entropy is going to increase. So entropy increase will be, so something like this. Okay, this is, so this is 500. Okay, so this is 500. Okay, this is 500. So entropy increase here is shown by this line. Please note that this net change in entropy will be this. This is delta S water. Okay, this is delta S water. Please note. So delta SW, this is delta Sg. Delta SW is more than delta Sg. Remember this, that all the heat given by the gas is received by water. Okay. So what is the total heat given by gas? Is this area under this. This is a process line. Entire area. This entire area will be heat given by gas. What is the heat received by the water? That will be, this is the water heating. So this entire area will be the heat received by water. These two areas will be exactly same. Okay, these two areas will be exactly same. Although they might not seem here, so I might do a little change. So you can say, yeah. Now that might convince you. Yeah. Okay. So these two areas, this area is the heat given by gas. This is the area heat received by water. They are same. Entropy changes are of course different. Delta Sg is this. Delta Sw is this. That delta Sw is more than delta Sg. Okay. Thank you.